Hey, welcome back. So, this week, I'm going to talk about mineral chemistry. Aren't you excited? You know, most people aren't too excited about talking about chemistry, and I think that relates back to their original chem classes. Everything I'm going to talk about today, you've seen somewhere before, but the problem is that it just gets swamped by all the rest of chemistry or whatever, and it's lost. But I think you're going to see today and next week that the chemistry related to mineral growth really understandable, really straightforward. And another plus for those of you that are taking geochem is that these first few weeks of class, both classes sort of reinforce each other. So that's nice too. Okay, well, there you go, right? Never trust an atom because they make up everything. Learning objectives for this week: briefly review some chemistry basics on atomic structure. Again, you've seen this before. List and describe the different types of chemical bonds. Well, you would have seen that before too, usually an intro. And then finally, discuss the factors that control the ionic properties of minerals. And what I mean by ionic properties is how the mineral forms, why it forms the way it does, the shape it does, what elements go where, that kind of thing. We'll start talking about it this week, and we'll work on it in more depth next week. Okay, well, it all starts with matter, right? And minerals are matter, and in anything that is matter, it has to take up some space, right? It has to occupy a volume of some sort, and it has to have mass. And of course, atoms and minerals, of course, are fit that bill. And of course, we're down here in the solid range of matter, rocks, right? Everything's cooled off to the point where everything is solid. And of course, in geology, we do liquefy things, right? When you get stuff hot enough, we can melt it. Or there's other ways of melting rocks, as you guys that have taken volcanology from me know, right? We can also flux melt by adding some sort of volatile to the mantle, or we can also lower the pressure. Gases, yeah, okay, there's some gases going on, but we don't really deal with them in mineralogy. And we're certainly not up here in the plasma range. But anyway, we know that the states of matter change as you add more energy. But we're down here in the solid phase. Okay, well, atoms. Smallest particle of matter that cannot be chemically split further. And of course, we can split an atom, but that's a whole different ball game here. And what they mean is that when you're breaking down compounds, all right, we can split the atoms apart when they dissolve and they precipitate or melt or whatever. But like melting something, you're not going to get the atom to go into any smaller. And what is an atom made out of? Well, it's basically two parts, right? You have the nucleus, and then you have this electron cloud. And the nucleus is composed of protons and usually, unless it's hydrogen, neutrons as well. So you have protons. Protons have a charge of 1, right? They're positive, and they have a mass of 1. So every time you have a proton, you're going to add a +1 as far as mass or +1 as far as charge. Neutrons, of course, no charge for neutrons, and a mass of 1 as well. So if we have a 1 proton and 1 neutron, we have a charge of 1 and we have a mass of 2. And then electrons, charges of -1 to balance out those protons, and no mass, I say. Do they have some mass? They are matter, so they have to have some mass, but really not enough to enter into any kind of calculations we're going to do. So just know that there is mass there, but not much. All right? So we've got the cloud of electrons, and as we'll talk about in a minute, these electrons are organized into shells, right? Remember that? Shells. Okay. So the electrons exist as this cloud of negative charges surrounding the nucleus of protons and neutrons. And again, these electrons are in shells. The quantum theory of chemistry here talks about these these different shells. Remember, there was the K shell that holds 2 electrons, and then we have the L shell which holds 8. Well, it's 2 shells really. It's an inner one with 2 and an outer one with 6. And then the M shell, right, that holds a total of 18. And I'm not going to make you do the electron configuration, that kind of thing. You're not going to be doing that for me, but you certainly will be doing it in geochem. So for those of you that don't remember, you'll get a good reminder there. Okay, something that's important to note is the outermost shell of electrons, whichever one it is, okay, is called the valence. These are the valence electrons. These are important because these are the electrons that in minerals anyway, most minerals, not necessarily the metals, but most minerals, they're the ones involved in bonding, and that's going to be important for us, right? So electrons are in shells, K, L, M, yeah, and the outermost one contains the valence electrons. No problem. Okay, so elements, right? Elements are, there's 92 naturally occurring elements, right? Each element, you can break it down, right? The smallest particle of an element that you can get is 1 atom, right? So you can have 1 atom of carbon, 1 atom of boron, 1 atom of oxygen. And there's 92 naturally occurring elements, although there are more that we have synthesized, and they don't stay around very long. But 92, right? 1 is hydrogen, and then all the way down at 92 is uranium. So, and these elements are organized in a periodic table so that those with similar properties line up. So all of the elements that line up in the first column, okay, have something in common. Do you remember what that is? Right? And as you go across the periodic table, right, column by column, something is changing. Hang on to that for a second, and I'll change the slide, and I'll get a bigger periodic table. Hey, there we go. All right. So, do you remember what it is? That when we start off in column 1, then we go to column 2, column 3. And if you said, well, that's how many electrons are in the valence shell, you would be right. So when we have hydrogen, lithium, sodium, potassium, rubidium, cesium, and francium, these all have 1 electron in the outermost shell. This group has 2, this group has 3, this group has 4, and so on. Okay? Now, this is an exception because this doesn't have, this is a filled shell, right? So the top row is the first shell. And remember, it's the K shell, it has 2. All right, so it's 1 and 2. Okay? And of course, the second electron in that first shell fills it. So helium has a filled outer shell, right? When we get to the second row, we see 1, 2, 3, 4, 5, 6, 7, 8. That's our next shell, and it's full with neon at 10, right? And of course, as we go down here, argon is full, krypton is full, xenon is full, radon is full. And those, of course, are the noble gases. And they're noble because they don't enter into any sort of chemical reaction with any other element. And why? Because the outer shell, that valence shell, is full of electrons. It doesn't need to interact. It doesn't have any motivation to gain or lose electrons, right? They're happy. All right, so anyway, the periodic table. A couple other things about the periodic table. The top number right here, 1, right? They've pulled boron out here to show you as an example. All right, we've got 5, that's the atomic number. There's the symbol of the element, and then the atomic weight or mass. All right, I think I've got this zoomed in on the next slide. But anything else I want to say here? Right, so number of elements, right, in that outer shell, and basically the rows are how many shells. Pretty simple. Well, nearly 4,000 minerals have been named. So that's a lot. And luckily, you won't have to remember them all. But here's what's nice. 92 naturally occurring elements, but only 8 make up about 90% of the Earth's crust. Isn't that great? That means that if you remember these 8, oxygen, silicon, aluminum, iron, calcium, sodium, potassium, magnesium, you get 90% of the periodic table taken care of, right? The Earth's crust, which is where we live, and it's most of the rocks you're going to find are going to be from the Earth's crust, unless you're digging up meteorites or something. And chances are they contain a bulk of these elements, right? Now, of course, the rest of the 92, if you can find them in any quantity, tend to be worth money because these are the common ones and those are not so common. So here we go. Right? Oxygen, by far, like I told you last week, makes up almost half of the Earth's crust, 46.6. This is an average for all of the crust. And then silicon makes up here 27.7. I think last week I told you 50 and 25. So anyway, 75% around of the Earth's crust is just oxygen and silicon, which is why the silicate minerals are the common ones. And, that's why most minerals are made out of oxygen and silicon, because they're the majority of the elements in the crust. And then when you look at the rest, right, again, iron, potassium, magnesium, sodium, calcium. So look at that little blue sliver there is all the other elements from the periodic table. So gold, platinum, boron, you name it, right? All the rest. Notice carbon, right? Carbon isn't on this list. Not one of the top 8 elements. All right, so back to the periodic table details here is the atomic number is the top number. And what's so special about the atomic number? Well, it is the number of protons in the nucleus. So if you have 6 protons, you're carbon. If you change the number of protons, you change the element, right? You can't change the number of protons and keep it the same element. Whatever the number of protons is the element that you have. And of course, that proton really helps to determine what the atom's chemical nature is going to be. Now, neutral atoms, like I like to say, an atom coming out of the factory, right? Like a car rolling off the factory, has the same number of protons and electrons to be electrically balanced. Okay? Now, it's not going to stay that way in many cases, and certainly not with rocks and minerals, but anyway, it starts that way. Now, the number at the bottom, so for here with carbon, it's 12, and this number changes, of course, is the atomic weight. And in order to get from 6 to 12, right, what are we adding to those protons to make that mass of 12? That's right, we're adding neutrons. So in this case, carbon 12 has 6 protons, always 6 for carbon, and 6 neutrons. Now you guys have all heard of carbon 14. Carbon 14 has how many protons? 6, right? So that means it has to have 8 neutrons in order to get to carbon 14. Sorry. Okay, and of course the atomic mass or weight, that's what's giving you the density of things. All right, so atomic number, atomic mass. Now we need to talk about ions as well, and ions are charged atoms. And you can get a charge by losing or gaining electrons, and you can also change your charge by turning maybe a proton into a neutron. That would also do it. But in our case, it's going to be basically losing or gaining electrons. So take a look down here. This atom is neutral, the first atom. It contains 6 protons and then 6 electrons. So it's electronically neutral. It also contains 6 neutrons. So it's got 6 protons, 6 electrons, and 6 neutrons. So its mass is 12, right? And it's not ionized. This is an example of carbon, non-ionized carbon, right? Same number of protons and electrons. Now, these two are ions. This one's negative, which is a anion. This one's positive, which is a cation. So here we've dropped the number of protons down to 5, but we've kept 6 neutrons and 6 electrons. So we've changed carbon now into boron, right? Because it's atomic number 5, not 6. But we still have our 6 neutrons and 6 electrons. But because the electrons and protons don't match, we have 1 extra negative charge. So this boron would have a -1 next to it, right? Meaning that it's got a charge of -1. Now over here, we've done the opposite, right? We kept the same number of protons as our original example, which means it's still carbon, but we've dropped the number of electrons to 5, right? So we've gotten rid of a minus, which makes us positive. So this one's going to have a positive charge of 1. And man, I know that this is elementary, all right? But it's good to go back and remember the rules before we start moving on. Because believe me, in a couple of weeks, we're going to get into stuff that's crazy, different than what you've ever learned before. And you're going to be kind of going, ooh, it's kind of nice when we had this little refresher course, right? Right. Okay, so this is all leading up to something, right? Talking about ions and things. And if you remember in chemistry, there was this rule called the octet rule. And that is that an element will tend to gain or lose or want a share of electrons until they are surrounded by 8 valence electrons, meaning the outer shell is full. All right. Now, with the first row in the periodic table, there isn't 8. There's only 2. All right. So 2. If you have 2, you're full. That's helium, right? But take a look at sodium here. Okay. It's atomic number 11, so it starts with 11 protons, right? It has to have 11 protons, and it has 11 electrons as well. Now, in this case, it's 22.99, so that means that this thing has like, 11 or 12 protons in its nucleus. We don't care about the, I mean, not protons, but neutrons. We don't care about the neutrons right now. So anyway, let's go back to the atomic number, 11. Right? So we have 11 protons, which means we have 11 electrons. Okay, so there's the inside shell, 2, the next shell, 8, right? That gives us 10, which means that in sodium that's electrically stable, it has this 1 lone electron in the outermost shell. And to say that sodium would like to get rid of that electron, it is an understatement. So let's go back and remember, what is sodium like, right, when it's electrically stable? What kind of material is this, right? And if you're thinking, well, sodium's a metal, right? Sodium is actually a metal. And is it a happy metal? Is it a metal that we could make golf clubs out of and airplanes and motorcycles? No. It's a really upset metal. It's a really pissed off metal. So much so that if you get a little water near it, what happens to it? Yeah, it explodes, right, and catches on fire. It's really reactive. Why is sodium so reactive? It's because of that extra electron out there. It has a high electronegativity. It wants to really get rid of that electron. So typically, if anybody else is around and will take that electron, sodium will give it up. All right. So when it loses an electron and now it gets a full outer shell, we have very stable sodium, right? So it's now chemically stable, but it's also turned into a sodium ion, right? A +1, because we got rid of the electron. So this guy's saying up here that in chemical compounds, atoms tend to have the electron configuration of a noble gas because they want to either gain or lose electrons so that their outer valence shell is full. So when we look on the periodic table, right, and you might remember from chemistry, this is the ionization potential, or what I just said, the electronegativity. How much does an atom want to gain or lose electrons? Okay? So transferring or sharing electrons that allows each atom to attain a full shell of electrons results in the bonding, right? This is what's going to stick atoms together and make minerals for the most part. And again, you'll remember, and we'll get to it in a minute, that there is ionic bonding and there's covalent bonding and a few others, but those are the dominant ones, right? Depending upon if you want to share or if you want to transfer. So when we're over here on the left side of the periodic table, these are the ones that have 1 electron, 2 electrons, 3 electrons in that outer shell. They're really going to want to get rid of those, some more than others. Okay? So they're going to be losers, which means they're going to end up positive, right? Those are going to be our cations. Over here on the right side, where we see things like oxygen, chlorine, sulfur, those guys have 6, 7 electrons in the outermost shell. They want to get 1 or 2 more to make them full. So they're going to end up gaining electrons, which is going to turn them into our anions. So for many, many, many minerals, right, it turns out that guys from this side, right, the left side, are bonding ionically with the stuff on the right side. And that's it. So here's the best example of all. Okay, I already told you about sodium, which is atomic number 11. So we start with 11 electrons, which leaves that one lone electron in its outermost valence, what it really doesn't like. Okay, so when we get sodium, and remember we said sodium is a pissed off, highly volatile, metal. Okay, when we get chlorine, now chlorine is atomic number 17, which means it's going to have 2, then 8, then 7, right? And it wants 8 in the outermost shell. So it's just as desperate as sodium is to gain an electron rather than lose one. And what's chlorine like when it's electrically neutral, right? What kind of material is chlorine in its natural state? And if you said gas, you would be right? It's a green, poisonous gas. They put chlorine in water to kill bacteria, right? Chlorine gas was used on troops in World War I, right, to kill people. So chlorine, in its electrically stable state, is a poisonous gas. Sodium is a explosive metal. But if sodium can give its 1 electron to chlorine, and they both become happy, right? He's got a filled outer shell, he's got a filled outer shell, right? And then these two basically want to stick together just because now sodium's positive and chlorine is negative. And man, that is you got to admit, that is totally cool for chemistry. To take an explosive metal and a poisonous gas, move 1 electron, and what happens? We end up with salt, right? Halite. The delightful substance to sprinkle on French fries and make nasty food taste good, right? Yummy. And your body craves it because it's electrolyte, right? So it's all perfect. That is the wonder of chemistry. And that, my friend, is an ionic bond. So ionic bonding occurs between elements on more or less on opposite sides of the periodic table. We've got the losers and we've got the gainers, right? So atoms gain or lose their outermost valence electrons to form ions, right? And ions are either positively or negatively charged atoms. Some are 1, some are 2, some are 3, some are 4. Okay. Ionic compounds consist of an orderly arrangement of oppositely charged ions. So when you look at salt, the solid, right? Basically, the reason that the sodium and chlorines are sticking together is some are -1 and some are +1, just like magnets, and they attract each other. Now, the reason for the cubic shape and the exact orientation of these atoms, that's a different story. That goes back to the story of, a little bit like when we talked about the silica tetrahedra. But don't go away, we'll get to that. Okay, so the reason the bonding is occurring because these things have opposite charges. So over here you can see these two atoms talking to each other, and the one says, "Damn, I lost an electron," and the other one said, "Are you sure?" He goes, "I'm positive." Okay, covalent bonding. Now, when atoms share electrons, not transfer them, we end up with covalent bonding, right? Covalent. The valence shell is the outermost shell. Co is meaning an electron is passing between two atoms. So here's what happens. We've got carbon, okay, and carbon's atomic number is 6. So it's going to have 6 protons, it's going to have 6 electrons. Well, 2 in the first shell, then 4, right, which makes up our 6. So how many does carbon want to have in its outermost shell? You're right, it wants 8. So it has 4, it wants 8. Now, no other carbon atom is going to give up 4 of its electrons and give them to another carbon. But what happens instead is each carbon can take one of its electrons, and I can share this electron with this atom, and I can share it with this one, right? So what that means is both of these think they have one more. And if you do that 4 times, so look at this guy here. He gets 1 from him, 1 from him, 1 from him, 1 from him. I don't know why these are all he's. Who knows? You know, maybe it's summer camp. I don't know. Anyway, they all get 1. So this guy has 8 electrons in its outer shell. It can't tell the difference where that electron came from. So that electron is swirling around this one, and it's swirling around this one, and that's happening everywhere in this crystal lattice. So every carbon atom is stable with 8 electrons in its outermost shell because it's sharing 4 with its nearest neighbors. And of course, its 4 are being shared, and it's getting 1 from each of its additional neighbors. Fantastic, right? That makes this structure very compact, very tight, with no weaknesses, and it gives us the strongest substance, right? The hardest substance that we have in nature, which is a diamond, okay? So diamond is a purely covalent substance and very, very, very strong bonds. And of course, you know, if we change the bonding, right, we wouldn't have a diamond. If we change the organization of the carbon atoms, we wouldn't have a diamond. But in this situation, we get something that's really strong. And this also says why carbon, because carbon can produce these polymers, right? Because carbon can add on to itself by sharing its neighbors, and it's very strong. You can make lots and lots of big carbon structures. And guess what? You, my friend, are a carbon structure yourself, right? So carbon is great at building things because it has this ability to covalently bond and make these long chains of carbon structures, right? So carbon fiber, nanotubes, this kind of stuff. Neat, huh? Okay, so we've had predominantly minerals are going to be ionic and covalent, but there's also metal bonds, right? We have metallic bonding. Now, we're not going to look at a lot of metals in this class, but if you go into economic geology, you'll end up running into a lot of metal, metallic minerals. But what's the story with metals? Well, you know, when we look at the unique properties of a metal, and I've got a crushed up piece of tinfoil here, you can see that metals have that unique luster, that metallic luster that we can identify them so easily with. All right. Metals are also malleable, right? You can pound them into these sort of shapes without them breaking. They're not brittle, right? And then the other thing about metals is that they have a high electrical conductivity. Well, all 3 of those properties, the metallic luster, the malleability, and the high electrical conductivity, is all due to the type of bonding that it has. And what you have to imagine is that just like I just talked about with covalent bonding, imagine that going on in metals. Because, you know, when do you have covalent bonding? Well, you have covalent bonding when you have either elements with low electronegativities, meaning they don't want to give up or lose, or they don't want to lose or gain electrons, you know, or you're bonding something with itself, like carbon or iron or copper, right? You can't lose and gain, you have to share. So metals are sharing, but they're not sharing their outermost electrons. They're sharing some electrons from some of the inner shells. And what that does is it leaves a sea of free electrons on the surface, right? I know that's a little strange to think about, but imagine if these atoms were bonded down deeper in their shells. And so the outer valence electrons, right, were free to sort of swarm. And think of this as sort of like bees swarming around a hive, right? So not any one bee is tied to any one place. They're moving and they're swirling around, ready to do their job. So when you try to break a metal, right, you bend it, as you pull these atoms, try to pull these atoms apart, new electrons can swarm in to fill those gaps and keep the thing bending and not breaking. So that's what causes the malleability. The luster that you see, the metallic luster, is that swarming electron cloud. That's what gives you the metallic look. And then finally, of course, in order to be conductive to electricity, you have to allow electrons to flow. Well, if you're in an ionic substance, there is no free electrons. All the electrons are tied up in bonding, and an electron cannot be broken loose to move, which is why if you shove a quartz crystal into a light socket, nothing's going to happen, or a ceramic or something like that. But with metals, there's all these free surface electrons that can get in there and start moving. And again, whether it's DC current or AC current, so that's why these metals work the way they do. So, a free surface of electrons on the outer part, and the electrons are tied together, the atoms are tied together down deeper, right? Metal bonding. All right, finally, there's a couple other types of bonding. You can get lots of hybrid bonds in minerals. That is, you don't have just covalent or just ionic, right? You have a blend between the two. And lots of minerals that we're going to see are a blend of covalent and ionic. And ionic bonds tend to be weaker, right? Covalent bonds tend to be stronger. But it all depends upon the surface. Now here in diamond, right? Diamonds are pure covalent substances, as we talked about before. Here's our other carbon substance, right? This is graphite. Diamond has a hardness of 10. Graphite has a hardness of 1, right? Do you remember Mohs hardness scale? Anyway, the sheets, right? Graphite is a sheet silicate, much like micas. And the sheets themselves are these ring structures bonded together, and those are strong. The little sheets are strong. Those are covalent bonds. But then the covalent sheets are weakly bonded to each other with something called a van der Waals bond. And van der Waals is really like static. So these sheets, and we'll talk about this when we talk about sheet silicates towards the end of the class, but the sheets themselves you end up with a slight positive charge on one side and a slight negative charge on the other due to the way these things are built. And just like you can get a balloon to stick to you, well, these sheets stick to each other weakly, which means that when you rub a pencil across a piece of paper, you can actually pull those sheets apart, right? They're that weakly bonded. So again, some minerals are a combination of bonds, and some minerals have very weak bonds. All right, well, finally here, we're going to talk about the determination of ionic properties. And again, this is really like how and why do the elements arrange themselves the way they do. We've spoken about why they want to get together, okay, ionically or covalently. But what controls the shapes that these compounds take? Why is halite a cube, right? That's halite over here with its chlorines and its sodiums. And over here, okay, this is a rhombohedron of calcite, right? We have calcium, we have carbon, and we have oxygen in there. And of course, they're very different shapes, and why is that, right? So the distribution of atoms, when they start to pack together and form solids, right, control the physical properties like bonding. What kind of bonds? How strong are the bonds? What's the form of the mineral? Again, is it a cubic? Is it rhombohedral? Is it hexagonal, right? How hard is the minerals? What kind of cleavage does it have? All of these physical properties are controlled by this type of bonding. And again, we're going to get into why this is the case. Well, it all starts with a discussion on atomic size, right? Atomic radii. And when you read the textbook, it's surprising that you can't take really a single atom and determine exactly how big it is. And that's because, well, the nucleus is set, right? That's got a given size, but the electron cloud, these electrons are swarming everywhere around, and they're not staying like contained within a specific area. I like to think about this like the Earth's atmosphere, that certainly as you go up and up and up, you get less and less atmosphere, right? And where do you draw the line? Where would you say the end of the atmosphere is? Because there's always going to be a few gas molecules sort of leaking out of the top. Well, you know, geographers or people, they will say, all right, it's where you have X percentage of air remaining, we're going to draw that line. And it's the same thing with atoms, is that certainly as you get closer and closer to the nucleus, right, you see a density of electrons. And as you get further and further from the nucleus, right, you'll see fewer and fewer and fewer electrons. But you really never go to zero. So at some point you got to say, okay, that's the edge, right? But you know what's nice is we don't really deal with atoms on their own, so we don't really care how big they are, do we? Not really. But it's just interesting that you can't just exactly get the dimension of a single atom. But using the techniques that chemists use, we look at a periodic table, and overall we can see that atomic radii get smaller as we go to the right. So if we start here with sodium, and by the time we go over here to argon, argon has a much smaller diameter than sodium. And we also see that in a single column, going from hydrogen up to cesium here, that atomic radii get larger and larger and larger. And if you will remember your chemistry, right, this is due to something called the effective nuclear charge, how much those positive charges are pulling on the negative charges. And again, this is all for stable electrically stable atoms, right? But we really don't have those, do we? We're always involved in one that's gaining or losing electrons. So let's go to the next chart. And it turns out that when you have ionic compounds and you have a chlorine smashed next to a sodium, you can actually do pretty well at figuring out what the radius is between them, because when they X-ray these things, they can see where the centers are, and they can see, and they just take the part way between them here, and they're able to get overall, right, a atomic radii, the ionic radii, right, for chlorine and for sodium. So what I've written is, it is possible, however, to measure the distance between the nuclei of a cation and its adjacent anion in an ionic compound to determine the ionic radius of one of them or both. So what this means is we get a pretty good handle, all right, on how big our ions are when we're stuffing them into these solids to make minerals. And it will come as no surprise to you that each atom has a radius that changes depending upon the valence or its oxidation state, right? So if you gain electrons, you're going to get larger, all right? So certainly, as we go down the periodic table, we're gaining more and more electrons because we have more and more protons, so atoms get bigger. As we go to now look what happens. The light gray here is the unionized version, okay? The dark center is the size after we have lost an electron, okay? So sodium, the dark one, is the size of the ion. The big one, the gray, the whole gray thing here, is the size before we lost the ion. So notice something. Go over here to chlorine, right? We see the original size was the light color. Now the size is the dark color. So look how much bigger chlorine is than sodium now, all right? So it turns out that, you know, our anions tend to be big and our cations tend to be small, right? So these things started, let's go back for a second and I'll show you that when you look at the original size of sodium, all right, versus something like chlorine, chlorine was much smaller than the sodium before they were ionized. But now when we get rid of an electron for sodium, it shrinks in size and chlorine gets a lot larger. So anions are going to be big, cations are going to be small. So here's a simplified table showing you some of the differences after ionization. All right, so look how much smaller lithium got, right? And sodium, potassium, and rubidium. The other thing you can notice is look at the ionic radii of all these things together. What's important to note here is that anything that's about the same size, nearly, is going to be able to substitute for each other in crystal structures. So when we see things like calcium and sodium, well, they're not that different. And so guess what's inside a plagioclase, right? We have sodium end member of plagioclase and we have calcium end member of plagioclase. But stuff that's really big and different, like potassium's never going to take the place of where a sodium would be. Potassium's never going to take the place of where a calcium would be because it's just too big. Okay, now, so we have ionic radii that are dependent upon the oxidation state, right? What's the valence? How many we have? Are we a +1? Are we a +2? Or are we a -1 or a -2? That's going to change the radii size, and then you have to factor that in if you know what you're building. But here's something else. The ionic radii, meaning the size of our ions, are also going to depend upon something called the coordination number. And the coordination number, or I like to say often just Cn, coordination number is equal to the number of nearest neighbors bonded to an ion. And I've got 3 examples for you here, all right? Now all of these, our little ions here, are about the same size. We've got an orange one and 4 green ones. Well, look at the 4 green ones. You know, if we smash those 4 green ones together, notice that the hole that's going to be left over inside there is much, much smaller than here where we have 6 green ones surrounding the orange one. So here's a coordination number of 4, right? It's got 4 nearest neighbors. Here's a coordination number of 6, and here's the coordination number of 8, right? And I think you can see that if you were to press all the green spheres together, that the hole here is going to be much larger than the hole here, and certainly than the hole here. And of course, as the coordination number increases, the distance between the atoms increases, and the ionic radii of the element trapped in there can expand some. So think of these ions as almost like a kind of like a foam ball that with it, to a certain extent, if the hole is bigger where that ion is going to fit, then the ion can expand a little bit. If the hole's not as big, it's going to squash down a little bit. So we can change our ionic radii a reasonable amount given the hole that they're going to fit in. So this is out of your textbook, and what this shows is, and if we can take just one example, let's go over here to sodium. And I know this isn't that clear, but you see sodium plus, all right? So that means it's +1, it's an ion, and these are the ionic radii in angstroms, right? 0.35, 0.36, 0.41, 0.43, and 0.49. So it goes all the way from 0.35 down to 0.49, and here are the coordination numbers. So if you have 4 atoms surrounding it, it's the small number. If you have 12 atoms surrounding it, it's the large number, meaning that sodium can range, right, that big of a distance depending upon how tight of the little hole it has to fit into. So if you're going to build minerals, you kind of got to know, you know, how big are the holes you're putting things into. But anyway, so just again, as the coordination number increases, the distance between atoms increases and the ionic radii can expand. So that's 2 things, right? The oxidation or valence state changes their size, and the hole they're going to fit into changes their size. So the coordination number in the radius ratio, right? This is the way we determine what ions will fit together depending upon their relative sizes. So if you give me two atoms, if you say, okay, Terry, oxygen and silicon make up most of the crust. Let's start with them. Okay, so I take oxygen, and in its normal state, it's 2 minus, right? It's lost, it's gained 2 electrons, right? Silicon, in its natural state, its ionized state, in geology especially, it likes to be +4. So it's lost 4 electrons to get to this point. So there's the sodium atom, or ion, and here are the oxygen ions. When you smash all 4 of those oxygens together and make them fit tightly, the hole left inside between them is just big enough to put that silicon in there, right? So it doesn't rattle around, it's not loose, but it's not too tight. And this is the secret right here. This is the reason that all silicate minerals are made out of the silica tetrahedra. It's a tetrahedra because that is the structure that fits tightly together when you bond oxygen and silicon. Okay? It's not because there's 4 times as much oxygen, so we went 1 to 4. The reason for the 1 to 4 ratio is their relative sizes of their ions. So we call this the no rattling around rule, and next week we're going to talk about Pauling and Pauling's rules. And Pauling was this is Linus Pauling, and he was the one that determined all of this. But anyway, it's called the no rattling around rule, and basically the surrounding anions, the larger ones, touch, and the cation exactly fills the void. And we can predict, based on the ions in question, what sort of structure they will build if you bring them together. And what we do is we determine something called their coordination number, right? And that's using something called the radius ratio. So you take the radius of the cation, always the cation on top, it's always going to be smaller, right? So we put it on top, we take the radius of the anion and we put it on the bottom. So here's silicon, 0.26 angstroms, oxygen 1.3, and you're always going to end up with a decimal place, right? Something less than 1, because the anion's always bigger than the cation. Okay, so anions are larger, so this number will always be a decimal place. Anyway, when we do the math, you come up with 0.338 is the radius ratio between silicon and oxygen. And there's a table. This table is in your book. You will also be provided with this table if I ever ask you to do this stuff on an exam. But when you do the math, you figure out, hey, this thing comes up, right, between this 0.225 and the 0.414, all right? Anyway, we end up with a coordination number of 4. Oops, sorry about that. Had a little breakdown, doggy breakdown. Anyway, so you determine the radius ratio, you take that number, you go to this chart, and you determine that in this case it lies between 0.225 and 0.414. That means that silica and oxygen will be in tetrahedral coordination, and you have a coordination number of 4. Easy. So that means it's going to take 4 oxygens to surround the silicon. We'll be doing this in a problem set that'll give you some practice. This is the diagram from your book. It's figure 4.4 on page 70, and again, it shows you not only the ranges and the radius ratios, right, but then it also gives you an example of the type of structure that was result. And of course here, the example that I just gave you was silicon and oxygen, where we end up in tetrahedral coordination. All right. The other 2 common ones are octahedral and cubic. Octahedral has 6 atoms surrounding an atom, and it's octa, 8, not because of the number of atoms that surround it, it's because the number of faces that you would see on a crystal, so that would ends up making an octahedron. And then here you get cubic because you have 4 and 4. All right, so there's that same chart, And again, I'll give you practice doing this with some unknowns so that you can try this on your own. But anyway, that's the first step in the building block of every mineral, is to take the ions involved and figure out what is their radius ratio and therefore their coordination number. And this is how we start to build all minerals. Well, the last thing that we have to provide, okay, once we build that first structure, right, we start to build these what we call coordination polyhedra, like this, silica tetrahedra. There's another step after this, right? So I say here that the relative sizes of the silicon and oxygen ions dictate the geometric structure that results, a tetrahedron. This is why all silicate minerals are built from this structure. But this structure cannot exist on its own since it's not electrically stable, right? It has an overall charge of 4. You see, there's 4 oxygens, each one of them has a -2 charge. That's a -8 overall for the anions. It's got 1 silicon down in there which got a +4 charge. So together this entire structure is still -4. So there is no silica tetrahedra that exists on its own. So somehow the next step in this process is to help neutralize that -4. So going a step further, the simplest way to neutralize that -4 charge would be to simply add 2 magnesium ions. Magnesium, when it's oxidized, ends up +2, right? So if we take 2 magnesiums and we stick it onto the silica tetrahedra, it cancels the -4 charge. And our final formula would be Mg2SiO4, which is the formula for olivine, right? That's how the forsturitic version of olivine is made. And I'm going to show you this with all the silicates, how they work through their various steps to make these different minerals. But I wanted to get this far on the first time to show you that the first step in the building of any minerals, right, is to look at the ions and determine their radius ratio and the coordination polyhedra that would result from that. And again, some minerals, there's lots of them in there, some they're simple. All right, so the relative sizes of cation and anions control the type of coordination polyhedra that results. Tetrahedra, octahedra, cube. Next week we're going to go further, right? So we made great progress, all right? And try not to forget any of this by next week. And then in mineral chemistry 2, we're going to pick it up here and we're going to continue to explore what controls the growth and chemical variation of minerals. We're going to basically go further and look at how the silicates make this happen, all right? And to leave you with this classic chemistry joke. All right, see you guys next week. Thanks.